Hi everyone, I'm Fizza, and today I'll be talking about interactive stroke-based neural SDF sculpting. So as you can probably guess from the teaser, the idea is that given we have a shape that is represented by a neural network, how can we actually sculpt it so that we get some desirable artistic edit? Um, so let's first discuss why we actually need to do this. So shape editing has been extensively researched and widely adopted in practice. And under the editing umbrella, there are a lot of operations like filtering, cropping, non-rigid transformations. But what we are focusing on is digital sculpting, in which the user uses a brush stroke to basically deform the surface, either carve it out or extrude it. And there are plenty of tools like Blender and ZBrush that offer real-time editing for mesh-based models, such as triangle meshes or chord meshes. So there's a very strong framework available for sculpting those. But recently, we have seen that there are other ways of representing 3D shapes, and that include compact neural network that learn the sign distance functions of those shapes. So now that we have this new representation which can compactly store the shape, we also need to know how to actually process it and enable similar interactive editing. And that is still a little unclear. So let's try to break down the individual terms in the title. So firstly, the sign distance function is simply a function that returns the shortest distance from a point in space to the surface. So if the surface is this circle, then for all of the points that are outside the circle, the sign distance must be positive. For points within, it must be negative. And then for points on the circle, that's exactly where the sign distance is 0. So it's a clever way of telling where exactly the shape resides. And this we can pair up with neural fields. Neural fields are networks or multilayer perceptrons that basically map some coordinate to a field value. For example, it could be a pixel that's mapping to the RGB value of at that pixel location. It could be a 3D point that's mapping to the sign distance function, and so on. The advantage of using these neural fields over other network architectures is that we are not bound by the resolution anymore. We don't have to send a fixed image resolution size or a voxel because we can now just send the coordinate and its corresponding value. So if we pair these neural fields with the sign distance functions, we end up with neural SDFs that just encode the shape encode the shape implicitly. And there's plenty of research around neural fields, especially the nerve that we are probably all familiar with. So now that we have these neural sign distance function, what we want to do is basically sculpt these neural SDFs. And once we are able to do that, ideally, we would want it to be done interactively because that's how a user would be doing it. And then if we can do that, how much control can we provide the user in a way that they can do something that's artistic? So given that we have some network that learns the sign distance function, and that, for example, over here represents some torus, we perform some editing operation on top of it that allows us to stroke this gem in the center and these taperings on the side to have a ring of some sorts. So some of the related works that we were able to find in this area, and the most prominent one was this 3D neural sculpting, which basically does spot modification by using these analytic radial brushes and modifying those points to create either a dent on the surface or a bump on the surface. And there is another work that's more generic, and it targets shape modeling using these neural generalized cylinders. So shape is broken down into several cylinders, and each of the cylinder, there is a neural field in those relative coordinates. And then complex editing operations such as stretching and twisting can be performed. What we consider as our baseline is the 3D-NS method, and we'll see how we differ. So what we try to do is basically emulate what a normal artist or sculptor does when they are working with clay. So in order to modify the shape, they basically draw strokes and using some tool. That tool in our case would be a brush, and that brush could be any custom brush profile that can be modulated based on how the user basically sculpts the surface. So one, we allow for strokes. Second, the the stroke. And we do this in an efficient manner, which, when we compare to a 3D NS implementation, gives us a 15 times speed up over it. And the advantage of this formulation is that we can achieve some versatile range of edits that a modeler would be interested in. So the method is very simple. The user defines a brush profile over here, and then on the rendered neural SDF, they basically define points where they want the stroke to lie. Those points are interpolated to form a smooth trajectory, and then this trajectory is sampled in that tubular region. And the corresponding deformation based on the brush profile that we are using is basically computed, and the MLP is minimally fine-tuned using this sample points and the corresponding deformation, such that now we get, after updating the rendering, we get the edited SDF. So in this case, we have this protruding brush profile, and we have this stroke that's along the neck, and it's darker in these corners and kind of fades away at the center, so that you can see in these collarbones that are generated that are more prominent at the edges and then kind of fade away at the center. So yeah. So for the neural SDF component, we just use the siren architecture over here, which is an NLP that uses sign activations. The method is actually agnostic to whatever architecture you are using, as long as you encode the sign distance function in some way. So this is what we use for the network. And in order to train the base shapes, we have very shallow MLPs, 2 hidden layers, 128 neurons. We train it for 1 million epochs to get the base shape. And for the loss, it is a weighted sum of these 4 terms. We try to first regress the SDF at that point, and then the SDF follows the iconal property, which says that the norm of the gradient of the SDF is 1, which is the second term over here. And then the third term is the normal, in which we try to reduce the cosine similarity between the gradient of the SDF and the normal at that surface point. And then the fourth term is the boundary. So the bounding box in which we sample these points at the corners of those bounding boxes, of that bounding box, the SDF value should be high, because the object is assumed to be in the center of the bounding box. So we collect these 6 basic shapes, and we train a neural field for each of the shape. And now what we need to do is to define a brush that we can use to carve. So the users can define any sort of analytic brush. It is a polynomial, or it could be just obtained by drawing some control points on a -1 to 1 window, and just interpolating them using a Catmull-Rom spline or any other spline that they prefer. This brush can be extended to a brush family by scaling it with the radius and multiplying it with a certain intensity, so that we can get a range of the brush of its extent and of its intensity. So we have like a subtle edit over here, and we have a strong, prominent brush with high intensity at the bottom right. And now for the stroke is also defined using a bunch of control points that the user draws on the rendered surface. And these are interpolated again using a Catmull-Rom spline. So we use 2 splines, one for the brush, one for the stroke. And for the stroke, it can be modulated as we go along. So the intensity, the brush intensity, is a function of the location that we are on the stroke. We can even modulate the radius so that our stroke kind of goes wide to narrow as we move along. Now that we have the brush and the stroke defined, we have this UVN coordinate frame that resides in this trajectory that basically defines the local control directions around the stroke. So U is the tangent direction along the stroke curve, V is the in-plane normal direction, and N is the surface normal direction. This is all we need to know in order to manipulate that tubular region. So for sampling the tubular region, we wanted to do it in an efficient way. So that can be done by sampling a handful of points along the stroke direction U, and then just offsetting them in the V direction by the radius that the user provides. So the V direction can just be obtained by taking the cross product of the normal, of the surface normal at that location and the tangent direction, And we have the offset direction. We just offset the points to have something like this, and that provides us a decent coverage of the region that we are interested in. So we observed that for typical strokes on these shapes, if we sample around 99 points along the stroke direction, 101 points along the offset direction, that gives us around 10,000 points in total to capture an arbitrary stroke in arbitrary stroke for its sampling. Now that we have these points sampled, we need to compute the deformation that is done when we apply the brush at this sample location. So we know that for all of the points on the surface, the SDF is 0 over there. And now, after applying the brush, the point P is transformed to point P dash by an intensity equal to which is equal to the brush value in the normal direction. So now we know that after the editing should be done, the point has been displaced the SDF has been displaced from P to P dash. So at the point location P dash, this is where now our 0 level set should reside. So that's what we use to add the deformation loss in our fine-tuning. And then we fine-tune it for only 100 epochs, and it can even be accomplished in lesser. But for this duration, we let the model fine-tune in this region, and then we are done. So let's have a look at some of the results. So these are some example edits that we can achieve using this editing pipeline. We have this torus that I just showed earlier, and it could be converted into a ring by drawing these 3 strokes. We have this pumpkin. We could create a Halloween pumpkin out of it by protruding the eyes, carving the mouth. And this frog is turned into a hybrid frog lizard. And then this sphere HPG has been inscribed onto it. And along the head of the bunny, we have this protruding stroke, and this bald guy has been given a haircut. So these are some things that we could do. But let's have a look at it in a more detail. So on the left, this is a curve for the brush. On the right, this is the curve for the modulation. So if we have a brush that cuts a deep dent, and then if we modulate it along the stroke such that it's in full intensity at the start and kind of fades away as we reach the end of the stroke, then over here you can see the cheekbone that's carved. It's deep over here, and it kind of fades away as you move towards the mouth. And then for this bunny, if we have a brush that looks like this 3 troughs and crests, and if we modulate it in a central fashion where it's maximum in the center and kind of fades away at the end, so if you see the brush along the stroke along the spine, it's prominent at the center and fades away at the edges. Same for the head. And then for this frog on the back, if we have a brush that looks like a negative sine wave, and if we modulate it again using a sine wave, we have this nice-looking braid at the back. And for this torus, if we have a brush that is non-symmetric, and it cuts a dent, but that dent is not symmetric, and it's modulated by a dampened sine wave, so then we have a pattern like this, which kind of is intense at the start and then fades away. And an artist would do this sequentially, so here we show that we can do that. We have this protruding brush that we modulate using this smooth sawtooth function, and we do it on the mane of the unicorn. So we have this fancy stylized mane now, and now we use a sine wave modulation with the same brush on the tail. So now the tail is converted into a Barbie-looking unicorn. And then now if we do not do any modulation at all, but just use a simple brush along the wings, then the wings already have a lot of detail on them. So all we need to do is just run the stroke through it, and we get these nice extrusions. So let's have a look at the qualitative results. So this is the ground truth that is obtained when we directly deform the vertices in that tubular region. And this is what we get when we apply our methods and use only 8 points along the stroke direction. And comparing this to 3DNS, if we use 8 sample points for the 3DNS spot modification, then we see these bumps, and it's clearly very discontinuous and not what we would want when we are trying to do a smooth sculpting operation. This coarse mesh result is basically the result of applying the same ground truth deformation, but on a mesh that has same number of triangles as the number of parameters in our network. So this quality is very poor because it's not sufficient. The number of triangles are not sufficient to capture the details that are in the bunny. These are some numbers. So we measure the chamfer distance between the ground truth mesh and our edited shape, and we also do this for 3D NS, and we also do this for coarse mesh. So we see that within the tubular region, the chamfer distance is significantly low compared to the other methods, which shows that the edit is being created very nicely. And over the whole surface, the difference is not that much, but it is still there. And that's because the rest of the surface requires some regularization to make sure that it stays where it's supposed to. And now is the timing part. We also want to make sure that we don't spend an obscene amount of time on it, because here we know that almost all of the neural methods, as soon as we hear the word neural, it comes that it would take hours to train, and we do not want that, especially with these sculpting operations. So if we look at 3D NS, and if we change the number of points that are used along the stroke, then 3D NS scales badly, and it takes around 8 seconds to create a stroke that has 128 number of points along the stroke direction. Compared to ours, which however number of points we vary, we usually do the whole edit within a second, and the gain is significant when it comes to using our method. And then we can also think about why we are getting this speed up, because since 3D NS is designed for spot modifications, the way they go about this is that at the point that the user clicks on, they create a disk around it and sample 120,000 points within that disk. And in order to simulate a stroke, n such points have to be sampled along the stroke direction. And this is very costly and not scalable at all, as we saw earlier. And also, some of the edits are impossible with this formulation, because the overlapping influence of these disks will make it impossible to get those modulation effects or get very sharp features. So if we do some performance profiling of our method, I'm not sure if this is visible, but most of the, within a fine-tuning iteration, most of the time is spent in sampling the data. That is around 60% of it. And the time is roughly divided between the sampling the surface and sampling the stroke tubular region. And within these two, the most time is taken by the surface projection step. This is the step that after we sample all of the points, we need to snap them back to the surface before we can actually do the SDF computation and brush deformation and everything. And this step takes the largest amount of time, because if we are using 4 steps to sphere trace and successively move closer to the surface, these are sequential and they cannot be parallelized further. So this is a point that we can think of to further optimize. As for the implementation details, this was all done on this laptop, which has a 4070 GPU. Implementation was done in PyTorch and OpenGL, and for mesh processing, there are the off-the-shelf libraries available that were used. But we also see the optimization potential by having actually a custom implementation, given that the sizes of these neural SDFs are small and they're pretty shallow, so we could benefit from custom CUDA kernels. There are obviously some limitations with this method, the first one being that we are dependent on the size of the network, the number of layers, the number of neurons. So if we have a model that is trained on a network that is very shallow, if we apply some high frequency brush on top of it, then it gets blurred and it loses the sharpness, as you can see over here. But if we use a higher size, like a bigger size network, and use the same brush, then we can see individual waves correctly showing up here. But then we also see these bumpy artifacts, and that is because of the need of regularizing the rest of the regions of the model. So these 3 are the key problems in order that need to be addressed before we can take this further. So for the future work, we could consider optimizing the training process using custom CUDA kernels for training. The other thing that could especially be worked on is to devise a better representation specifically catered for geometry rather than using these generic MLPs as the underlying architecture. And the thing that seems the most appealing to me is to figure out a way to localize the updates when we are editing a particular region. Right now, a neural field is completely global. So changing or slightly perturbing the weights can result into some completely unexpected edit. So we have to resort to fine-tuning, even though it's minimal, but we still have to do it. If there's a way to somehow link the weights with the region, with the surface region, for example, using some wavelet-based representation, that would be ideal. And then we also want to preserve the sharpness of the rest of the surface that we are not touching, and we don't want to regularize those regions because we are kind of wasting our point samples. So another option could be we could actually consider neural SDF intersections where we have a bunch of neural SDFs and we use the Boolean operations that we use in constructive solid geometry to apply the same processes here and get those sharp edits. So for the conclusion, we believe that editing neural fields is still underexplored compared to representation part of it. And ideally, editing the neural fields should be at least as on par with their discrete counterparts, and if not at the same level, but it should at least be responsive in a certain way. And our work was one such attempt to enable interactive sculpting of neural SDFs, and there's still plenty of things to explore. But yeah, this is all. Thank you.
Thank you, Fizza, for the presentation. Let's move on to our Q&A. Oh, OK, someone there.
Hi, really cool presentation. I have maybe like a high-level question, which is like, what is the benefit of doing the sculpting on the neural representation directly instead of sculpting in the traditional way and then using the finished product, making a neural representation on the finished product after the fact for rendering purposes?
That's a very good question, that why do we even want to do this? So the first reason is that if we want to consider something as a complete representation, then we need to account for all of the things that could be possible with it. And one thing is the editing part, that if we have a way to compactly store something, then we would also have a way to compactly edit it. And that was an attempt to explore this. And secondly, regarding training, applying the strokes on a mesh, and then at the end converting it into a neural SDF, that would be, if you're considering it from an artist's perspective, that would be a very back and forth process, because usually it requires several iterations of sculpting to reach the final product. And if you dump everything into a neural SDF, then you'll have to apply marching cubes again to get it back, and then do the back and forth in order to get your desired edit. So there should be something within the framework that allows you to do that.
Cool. Do we have another question? OK.
Really cool work. Thank you. I was curious, you touched on one of the slides on the details, like if you have a small network, there is not enough details sometimes.
Yeah.
I was wondering, do you have any insights on how big the network should be to represent the higher frequencies, and basically the Nyquist relationships between the network capacity and details?
Right. So this network over here, it is 128 hidden layer size with two hidden layers, and that's what is used to represent this frog at this level. if you want to get more details, for example, the line around its mouth, then we have to resort to more either a deeper network or a wider network. And that usually depends on the level of detail your model has. And with regards to sculpting, there could be advantage in using a shallower network rather than a deeper one. So it depends on how your shapes are.
Thank you.
It was a great talk. I really liked it a lot. Two things. One, have you played with the extreme situations where your surface, disruption is almost as big as your object? Does it really distort, or does it play nice? And the second question is, have you thought about, does the setup and then the stroke have to happen sequentially, or can you do them out of order?
So for the first question, yes, we tried using a brush of extremely large intensity, and there's a point until which it works, and after that it breaks because it affects the other neighboring region, and there's a limit to what the regularization can keep in control. So after that, the SDF kind of explodes. So there is a limit to how much we can increase the radius or how much we can increase the intensity. Regarding your second question, could you repeat?
It sounds like there's a brush that happens after you've set up the heuristics, but they shouldn't have to be in order. Like, you should be able to brush on the frog, for instance, and then adjust it afterward. Is that right?
Yeah, they don't have to be in any specific order.
And so if that's true, it'd be interesting to see there's an animation perspective that you could use with this as well.
Yeah, I'll consider that. Thank you.
I think we have time for one last one. Okay.
Thanks, it's really fascinating. But for someone who's quite ignorant of this sort of thing, to actually evaluate the network, how many floating point operations would you actually need, say, per sample calculation of the SDF?
So if you consider a network of size 2 hidden layers and 128 neurons, then that is a 128 by 128 matrix, 2 multiplications of 128 by 128 matrix, and then 3 by 128. So I can't do the math right now, but that's three matrix multiplications of, you can imagine, of size 128 by 128 to compute a forward pass.
Okay, thank you.
All right, let's thank our last speaker again. And